शांति शांति।
वर्दे वीणा वादिनी वर्दे, काट अंत उनके बंधन स्तर, वहां जननी ज्योतिर्मय निर्झर, कलश भेदतम हर प्रकाश पर, जगमग जग कर दे वर्दी वीणा वादिनी वर्दे। Namaskar. I welcome you all to the two-day National Conference on Recent Trends in Material Science and Nanotechnology, organized by Department of Physics, IIS University, on January 18 and 19, 2019. The conference provides a perfect symposium for scientists, engineers, faculty and students in the field of material science and nanotechnology to meet and share their knowledge. This scientific program aims to pave a way to gather visionaries through the research talks and presentations and put forward many thought-provoking strategies. We envision to provide a premier technical forum for reporting and learning about recent trends and developments, as well as for launching new applications and technologies. I once again welcome you all. Flowers are a proud assertion that a ray of beauty overvalues all the utilities of the world. May I request Dr. Rishabh Gupta, Honorable Vice Chancellor, IIS University, to present floral greetings to the keynote speaker of the conference, Dr. T.K. Awasthi. Thank you, sir. May I request Honorable Vice Chancellor of the University to kindly deliver the welcome address.
Namaskar. Professor D.K. Awasthi, keynote speaker of this conference, Professor Y.K. Vijay, Professor S.N. Joshi, Professor Arun Pratap, other dignitaries, scientists, academicians, young researchers, and students who are here at the conference on recent trends in material science and nanotechnology. It gives me immense pleasure to welcome you all to this conference in a university which is not very old. IIS, deemed to be a university, is among the pioneer institutions for women education in Rajasthan, imparting high quality education. It is known for excellence in delivering value-based education to students and encourage them to think innovatively in different walks of life. It particularly focuses on preparing students to become world-ready citizens who are abreast with any professional and social challenges they might face in an educated and empowered mind. Material science and nanotechnology are evolving consistently, and they continue to initiate and pave the way for new theoretical concepts and research in areas of physics and engineering. I am sure that through the different range of scientific sessions and topics, most of the aspects of material science and nanotechnology will be covered, which will give you a broad experience to explore, grow and contribute to the society. I am confident that the 2 days of the deliberations will help in conferring knowledge on the new technologies and the latest drift in the domain. With these thoughts, I accord a very warm welcome to all of you and dignitaries sitting on the dais, that is Professor K. Sharma, Professor Pradeep Bhatnagar, Dr. Nidhi Bhargav, and our Rector and Registrar Rakhi Gupta, and dear students. So once again, I welcome you all to this conference, and I am confident that this conference will prove to be a grand success. Thank you.
Thank you, sir. May I now request Professor Pradeep Bhatnagar, Dean, Faculty of Sciences, IIS University, to give us an overview on the Faculty of Sciences at the university.
Namaskar. Dr. Awasthi, Director of the MIT Institute of Nanotechnology, Noida, Honorable Vice Chancellor, Professor K. Sharma, Dr. Nidhi Bhargav, resource persons, delegates and the students. On the behalf of myself and the Faculty of Science, it's my pleasure to welcome you all in this 2 days national conference, which is being organized by the Department of Physics of our university. Under the science faculty, we have departments of environmental and life sciences, which include zoology, discipline like zoology, botany, biotechnology, microbiology, environmental science, and the departments of home science, Department of Chemical Sciences, Physics, Statistics, Mathematics, and Geography, and the Computer Science and Mathematics. This faculty is strengthened by the strong 72 faculty members. Laboratories of all the departments are very well equipped with modern equipment and are recognized by DSIR of DST, and the university has CPC SEA recognized animal house facility also to carry out the research in the field of reproductive biology and the toxicologies. We have R&D unit also having facility of animal cells culture along with other modern equipment to carry out the research in the molecular biology and the genetics. The faculty is actively engaged in the research along with the teaching at the PG, UG level and also supervising research for the PhD students. Since establishment of this university, 63 students have been awarded PhD degree in the science faculty. During the last year, that is 2017 and 18, the faculty has published 65 research papers in national and international journals. At present, we are running 2 projects sanctioned by the Rajasthan DST and the DBT Government of India, Delhi. Our Department of Physics has an infrastructure with well-equipped laboratories and resources. Physics department has made remarkable progress in terms of quality of research and towards the excellence in the teaching under the able guidance of our advisor, Professor K. Sharma, who is also from the physics streams. The department offers PhD programs in nanotechnology, computational physics, and microwave electronics. The Department of Physics is very well equipped with microwave lab with 4 experimental benches in the X, C, J, and KU benches. Thermal evaporation unit for the thin film deposition is also available in the department, along with the computational lab, which has 15 desktop loaded with YENX2, K, Quantum, Espresso, and P Spice Meta Labs, to name few. I am confident that these 2 days of the conference will provide a motivation to our young researchers, young faculty to carry out the research in the different fields of physics. Particularly, I am interested in nanotechnology because you know the nanotechnology is covered all streams of the science, physics, chemistry, biology, etc. Thank you so much and welcome once again.
Thank you, sir. To give us an insight into the aims and objectives of the conference, may I please call upon Professor K. Sharma, advisor to ICE University and the conference director.
Namaskar, Professor Dwivedi, Professor D.K. Awasthi, keynote speaker of the day, Director, MIT Institute of Nanotechnology, Honorable Vice Chancellor Dr. Ashok Gupta, Dean Faculty of Science Professor Pradeep Bhatnagar, Dr. Nidhi Bhargav, Dr. Ritu Jain, Registrar Dr. Rakhi Gupta, and the scientists present here, Professor Y.K. Vijay, Director VGU, Vivekananda Global Institute of Technology, Professor S.N. Joshi, Senior Scientist from CD Planning, Professor Arun Pratap, MS University Baroda, and other dignitaries present here, faculty members, delegates, students. today, this conference, the recent trends in material science and nanotechnology, this was culminated because of the importance of this topic. Actually, this topic is a multidisciplinary topic in which the research is going on world over. Physicists, chemists, biologists, doctors, engineers, and people from other walks of life, they are carrying out research work. So much so that there have been, say, principal projects in the states like United States of America, Japan, European Union. Billions of dollars is being spent in this area for industrial outcomes and applications like wrinkleless garments, robotics, drug delivery, etc., etc. So looking to the wide scope of this field, this topic was chosen. Moreover, at this university we have as Professor Bhattnagar has just introduced, that we have a full-fledged laboratory of software loaded with Bean2K, Quantum Espresso, PSPice, MATLAB, etc. And moreover, thermal evaporation unit has been installed in 2 years back. So the research is going on. This was a current topic for the department, as well as this is a current topic of importance for people from various walks of life. So therefore, this conference was culminated on this topic. Now, Richard Feynman first talked about the synthesis of atoms for cluster formation in 1959, and the term nanotechnology was first used by Norio Taniguchi in 1974. However, at that time the apparatus to peep into the material was not up to that accuracy that we could go up to the nano scale, 10⁻⁹ meter. It was limited up to the micro scale only, and it was in that era that the computer chips, the integrated circuits, tunnel diode, etc., such devices came to existence, and the search was for smaller and smaller, but it could be possible only in 1981 with the invention of the devices, scanning devices such like scanning tunneling microscope in 1981, atomic force microscopy in 1986, which made it possible to visualize the material at atomic level. So only with these, when these instruments came to peep into the material, only then it could be possible to go to the level of 10⁻⁹ meter. 9 meter means nanometer. Actually nowadays the materials or the particles of the size of 1 nanometer to the 100 nanometer are covered in this nanotechnology. So meanwhile, one thing more happened. In 1985, the buckyball, what we call as fullerene, was discovered. So that was a carbon material with 60 atoms. That unit was discovered, and that was followed in 2004 by the discovery of graphene, and then formation of nanotubes, etc. So that gave a movement to this area to research in the nanotechnology, and so the people are working here. At this scale, the properties of the material, when we go to nano scale, the properties of the materials change a lot. Their strength changes, electrical property change, thermal property change, and catalytic property change a lot, and even the physical appearance changes, such like the copper, which is opaque, it becomes transparent at nano scale. Similarly, aluminium, which is stable, becomes combustible at nano scale. Similarly, gold, which is insoluble in water, becomes soluble in water and forms the colloids, and when the size of the particles is greater than 100 nanometer, it shows the color purple color, whereas when we go to size less than 100 nanometer, it becomes red. So these are certain characteristics, that physical characteristics, chemical characteristics, and other characteristics change a lot when we go to that scale. So therefore people decided to investigate this scale of the materials, and now there are research is going on. Physicists are trying to investigate the solar cells with better efficiency, lithium-ion batteries, supercapacitors, etc., etc. Whereas the biologists, they are trying to the drug delivery at the proper point where the drug is needed in the body. Moreover, the molecular level motors, biological motors is in focus to be devised. So the life sciences, they are taking it at a great scale. Engineers are trying to develop nano robots, and similarly in photonics there is a great use biosensors, filtering of water, purification of oils. These are the such areas where the researches in nanotechnology is currently in focus and going on. So the nanomaterials, they are also being used by engineers for other purposes, for strong materials, say for aircraft, for civil aviation. Similarly, strong material for the nanoparticles, this graphene, say, this is harder than steel. So this can be used for defense purposes, etc., etc. So such investigations are on, and the physicists are on the move to develop, say, nanophotonics, nanoionics, etc., etc. So these are the certain areas where the researches are going on, and there are many more areas which you will be able to know in next 2 days when you interact with the experts. There is one more dimension of this field, that is that at this scale, when we go to nanometers, the particles become, the quantum nature of particles become prominent, and therefore the theoretical investigation also becomes important. And for theoretical investigations, the density functional theory has come, with the help of which it has become possible to devise codes for investigation of electronic structure of materials. And nowadays there are several codes like Wien2K, quantum espresso, VASP, crystal, etc., etc., which are being used for investigation of nanomaterials theoretically. So this is the other dimension of the subject. So with this a brief glimpse of the subject, which will be elaborated in the conference, I would like to inform you that there are about 100 delegates from different parts of the country which are participating in this conference, and more than 10 resource persons have very kindly consented to come over here. We are grateful to them. They have spared time out of their busy schedule to make this conference success. And I will appeal to the delegates to interact with the experts and put questions so as to find out solutions to their problems, so that this conference will be beneficial to them. And I wish all success to this conference. And if there are any lapses on our part and some arrangements, I suppose you will forgive us. And once again, I am grateful to the key person and the other scientists present here. They have spared time. We are very much grateful to them, and especially to Professor Y.K. Vijay, who has been a guiding source for us and the management of this conference. And I am also grateful to the Vice Chancellor, Dr. Ashok Gupta, and Registrar Dr. Raki Gupta, who have cooperated at every step to make this conference a success. Thank you very much.
Thank you, sir. It is a proud privilege to welcome and introduce our keynote speaker for the conference, Professor Devesh Kumar Awasthi. Presenting Director, Amity Institute of Nanotechnology, Amity University, Noida, Professor Awasthi has an array of research achievements. With over 3 years of experience in Defense Research Development Laboratory, Hyderabad, as scientist, he has served as Scientist H and Head of Material Science and Radiation Biology at IUAC Delhi. With over 500 research papers to his credit, Professor Awasthi has H factor as 47. He is a Fellow of Institute of Physics, UK, and the Founder President of Iron Beam Society of India. with a series of international collaborations with research groups in NIMS Tsukuba, Japan, CSN-SM Orsay, Kiel University, LMU Munich, MPI Stuttgart, Germany, St. Petersburg, Russia, and Padova University, Italy. He is the Associate Editor of international journals Radiation Effects and Defects in Solids by Taylor and Francis and Vacuum by Elsevier. Professor Awasthi has to his credit a book on swift heavy ions in materials engineering and nanostructuring. We welcome you, sir. I now invite Professor D.K. Awasthi to kindly deliver the keynote address.
Dr. Ashok Gupta, Dr. Bhattanagar, Dr. Sharma, Dr. Nidhi, Professor Vijay, Professor Joshi, Professor Arunantara Pratap, and the faculty of the university and students. I am very pleased to be here. A very good morning to all of you, and I am very pleased to be here, to be with you, among all of you here, students bubbling with energy and seeking more and more knowledge. And you are the power, female power, and you have a lot of challenges in the country, and some of the things I will discuss. And this is you people who have to solve these problems. So what I have planned here is to talk of nanotechnology for sustainable society. We do a lot of research, and research is of two kinds: basic sciences, trying to understand the things, science, and then trying to apply for the society. So it's a fundamental research or the applied sciences. So what I will talk will be a blend of the two, whatever we have been trying to do, and some of the things are in certain directions of sustainable society. So my plan is can you please do from there? Yeah, okay. Thank you. So, introduction, a little bit of introduction, and then we'll see that how the introduction, nanomaterials for energy, healthcare, water and environment. And nanomaterials just now was briefed here. And are you aware of nanotechnology in your subjects here? Yes or no? Little bit. So that's fine. So I need not go into very introduction of it. I assume that you are aware of nanotechnology or nanomaterials. Then we'll see the role of nanostructures in these materials for energy. And there are different kind of sources. I'll be picking up some of them. It's not possible to talk everything. And water and environment remediation by nano, and a bit on healthcare, and in summary. So that's my plan. Goes in this direction. Yeah. Okay. Yeah. So this is very clear that the needs of society is basically air, water, energy, health and security. So you know that for living, what we need is, first thing is what air. If you don't get air for, let's say, half an hour, then we'll die. Okay, so air is the most important part. Then water. If you don't get water for a couple of days, then you will not survive. But both of the things are getting polluted by ourselves, our own society, which needs to be, some remediation plan has to be there. Then energy. So we need electricity, power everywhere, without which it's difficult. So, and these energy sources are depleting fast, and therefore there are a lot of alternative energy sources, and this is what we will see. We also need that our health should be fine, then only you enjoy living. So to be healthy, if there is some disease, there are two things one has. First to diagnose it, that what it is, so diagnostics. Then once you know what it is, then therapeutics, that means you solve the problem by medicine or surgery or whatever. And the security or defense, that means we want our own security of the country, so the defense is important. So nanotechnology has role everywhere, so it's a very, very important area. And I am very happy that the university has taken a step to organize a seminar or workshop on this particular issue. It's very interesting, and I must share that as I see, and that you are in a very good hand, all students are in a very good hand in the dynamic leadership of Dr. Gupta, the advisor, dean, and the very qualified faculty. So you are at a very right place to learn the things and to go ahead in the life. So in the materials for energy, basically, there could be the solar energy is the first thing, and there are a lot of efforts going on where the nano has a role. But I will not be talking in all of the things because it's difficult to cover everything. So thermoelectric is something where you utilize the waste heat in the factories, and there are a lot of boilers which are at very high temperatures. So you can utilize that. One can utilize that heat in useful manner. For example, in car, the engine gets very hot. So now there are devices that you put the thermoelectric thin films on engine, and then utilize that power, the heat, waste heat, to convert into electricity, and that is utilized within the car. So that things using the nanotechnology is already there in certain cars, BMW and Mercedes, and this German cars are having this kind of things. Hydrogen storage and photo spreading of water to produce hydrogen. So both of things are important because hydrogen is another source of energy. There were a lot of work being done in Rajasthan University by Professor Vijay and his group in this direction. Biofuels, the supercapacitor, fuel cell, thermal storage. One can actually utilize that heat. You store the sun heat in some form. We will discuss that. And nuclear materials are also important. So in the whatever I put in red, I will be touching upon some of those things. So I will just come to very basic thing. You are familiar with this thermoelectric materials. In a Seebeck effect, you are familiar that if you have a temperature difference between the 2 points, and they are having a temperature difference of delta T, that means one end is at temperature T, the other end is T plus delta T, then there will be a potential difference between the two. And then the Seebeck effect is that you get some voltage, and you have this thermal power which you get this delta V by delta T. And the Peltier effect is just opposite of that. That means you put the potential difference, then you get the temperature difference. And this actually can be, the thermoelectric efficiency can be quantified by this factor, ZT, that's the, let's say, efficiency, and S square sigma T by K. S is Seebeck coefficient, and sigma is electrical conductivity, and K is thermal conductivity. And it is very clear that if I want to maximize ZT, then I should have a large Seebeck coefficient, high thermal conductivity, high electrical conductivity, and low thermal conductivity. But there are problems because these three things are actually interconnected. So what should be the strategy to do it? The aim is to maximize ZT, and this can be done in this way, that the thermal conductivity can be actually splitted in this form, that you have the electronic thermal conductivity, then phononic part. So one actually, if one reduces only K phonon, then one can reduce the K. Okay, one can always say that okay, I can in this formula here in this formula, if I try to reduce K to increase ZT, then this also decreases, because thermal conductivity and the electrical conductivity is correlated. So this is what I am telling you, the strategy is that the two are connected by this formula. Electrical conductivity and thermal conductivity is connected by this formula, and it is independent of K phonon. So you reduce K phonon, not Ke. So if you reduce K phonon, then the electrical conductivity is not affected. Okay, you decouple it, and this is the strategy we used to improve upon the ZT. Okay, so how can one do it? This can be achieved by distorting the cells. That means you will introduce the point defects and vacancy and do alloying. So if this kind of defects are there, then one can lower down the thermal conductivity. Or you take the complex crystals like this, which are rattling molecule. So in this kind of things also, you have a lot of electron phonon scattering, and you have lower thermal conductivity. And or you use the nanocomposite in nanostructure form also, you have lower thermal conductivity. So we have actually, I was in ion beam laboratory, so we try to utilize those things. And why ion beam? Because ion beam has a special feature that it actually deposits a huge amount of energy density. Suppose this is a film and the ions are coming here. Ion comes from an accelerator. Ion is basically an ionized atom having a lot of energy, and when it is going inside here, it is actually depositing a lot of energy. And by these two processes, I don't go into detail, but the result is it can produce defects. It can induce interface mixing, which I will show you later, and it can produce nanostructures. So some of these things were required actually when we see at the back that what we need is creation of point defects and creation of nanostructure, and both the things I am getting here by ion beams. Defects I am able to get and nanostructure I am able to get. So that is how we want to lower down the thermal conductivity and improve upon the efficiency. Okay, so now ion beam synthesis of thermoelectric material thin films. So this could be done by ion beam mixing or ion beam induced mixing. I'll explain the difference between the two. And by ion irradiation also one can improve the thermoelectric thin films properties by inducing the nanostructures in that. So this is what is done here. You have one film here, one material and another material. You shoot the ions here like this. So what can happen? It can produce defects. So these are regular structure, but now it has a lot of defects here and a lot of defects here. And now when you annihilate at higher temperature, then they get mixed here. So you get a mixed compound here. And so this is called ion beam induced mixing in this way. It can also happen that just after this you directly go here. So this is called ion beam mixing. So the difference is if you get directly from here, then it is ion beam mixing. When you go through this annealing, then it is ion beam induced mixing. So I'll show you the cases here, two cases here. Lead telluride is a well-known thermoelectric material, and we try to make it. So we deposited tellurium on lead, 2 layers, and you have a thermal evaporator here. One can deposit these two things. Okay, but the thing is, when we deposit lead, it is always oxide. Whatever vacuum you have, there is enough oxygen to oxidize it, and you get lead oxide. So this is the pristine. You can see that you have tellurium and lead oxide. If you heat this system, then you get tellurium and lead oxide only. You don't get lead telluride. If you heat this tellurium and lead oxide film, then again actually lead oxide increases and tellurium remains tellurium. There is no mixing between the two. But when I actually irradiate, then you can see you have lead telluride here, complete lead telluride. So this complete thing had converted into lead telluride, and this is the proof of that. This is the transmission electron microscopy. This selected area diffraction pattern. You get all the rings due to lead thermite formation. So this is the confirmation from X-ray diffraction and transmission electron microscopy. So here what I have shown is that you are able to get lead telluride by ion beam irradiation, by ion beam mixing process. And I said that important thing was to have nanostructures in thermoelectric material. And there was a Nature paper actually, a science Nature paper, Hoshman. He said that nanostructure formation lead to enhancement thermoelectric properties. So we wanted to see what is kind of the morphology of our films. And it was very nice to see that they were actually nanostructure. You can see in the beginning the film was like this. And then when you irradiate, you get this kind of structures which are basically nanostructures. So that means you are having a nanostructure thermoelectric material. It is supposed to have better qualities. Okay. So we did some measurements on this. So this is, let us concentrate on this. Here you use the thermo power. And this is at the thermo power at different temperatures. So you have, this is for the pristine. This is, if you anneal the same thing, then it is here. But if you do the irradiation, then it's a formation of lead telluride. Then you see it is gone up here. So there is a clear cut that you are gaining the efficiency in the thermo power. I take one more case here. Here we have taken cobalt and antimony. Again, this can be done with the thermal evaporator. And then if you heat it, you get some alloy here, cobalt and antimonite. But then something will be unmixed here, which is here and here. But if you actually do irradiation here in the same thing, and then you do annealing, you get complete alloy formation. So that is the advantage. And another advantage you will see in the results here, that if you have this cobalt and antimony, you can make three phases: CUSB, CUSB2, CUSB3. The best for thermoelectric is CUSB3. Okay. So here we see that in irradiation and annealing, you get CUSB3 phase here completely in this one here. Okay. So that means in certain condition you are able to get a good quality thermoelectric thin film CUSB3 which you wanted. Okay. So this is the ion beam processing of materials to get the desired things. And this is same thing again being seen by a different technique. So you have CU and SB, and then after irradiation and annealing you get the CUSB3 here completely. And these are the Rutherford backscattering spectra, which shows the formation of that there has been some mixing at the interface. It shows that only, but the previous slide has shown that there is a phase formation by X-ray diffraction. And again in this case too, you have this flower kind of structure which you, when you blow it up, I mean magnify it further, you see that they are basically nanostructure. So this is what the assumption we started with, and we are getting the same thing. So these are very good thermoelectric thin films. Okay, so this was about thermoelectric thin films from academic point of view, because ion beam will not give you solution which you can apply, because it's a very expensive process. It cannot be economic feasible. One has to actually, although there are ion beam processes of say P-type doping, N-type doping, and they are all done at a very large scale using the ion implanter. They are basically accelerators, low energy accelerators, and they are all over used in semiconductor industry. Whatever you see in semiconductor industry, it is done by ion implantation. But in these materials, it has not gone to that level. So plasmonics to boost hydrogen generation by photoelectrochemical process. And plasmonics, are you aware what is plasmonics? Plasmonics deals with the basically in the noble metal nanoparticles. So it has a special property that it absorbs light at certain frequency, certain wavelength, and that will be clear by next slide here. If you have a metal particle, you shine with the light. This is a noble metal particle, and light is nothing but electromagnetic wave. That means you have electric vector which is oscillating, which is shown here and here. So when an electric vector is this side, the electron cloud goes one way, and when the electric vector is this side, it goes the other way. And when the incident light frequency matches with the plasmon frequency of the metal particles, then there is a huge absorption. So, okay, plasmon frequency a word I used, but I didn't explain what is plasmon. The plasmon is basically collective oscillation of conduction electrons, and they will have a fixed frequency. That's what is called plasmon frequency. And this surface plasmon resonance could be actually tuned. You can change the frequency by nature of metal, cluster size, what size is there, what is the shape of this, and they are buried in certain matrix, so it will be decided by the dielectric property of the matrix also. And I'll show you some result for that. Here again is the ion gun used here. You have a metal pieces here, and then zinc oxide matrix here, and you shoot the atoms by a source. Then you get the sputtering of atoms and molecules from gold and zinc oxide, and by self-assembly process, this is the metal embedded in zinc oxide is formed. Okay, this is possible in some way by in thermal evaporation also, if you do simultaneous evaporation by two sources. And then you can actually get, if you see the absorption spectroscopy, then you get one peak here, which is due to the surface plasmon resonance. Gold has a surface plasmon resonance. This peak is because of that. And by changing the temperatures, this can be tuned, this can be increased and so on. And at certain conditions, you get zinc oxide rod with the gold sitting on the top of it. This is further, on this further study is done, that you do the IV characteristic of it in dark, then you get this curve. When you shine light, then this current increases, which means that actually you are able to create more current, more electron in the presence of light. That means it has the capability of producing more electrons in the circuit, and this is shown here. Current is here, when you shine light it goes up, you remove the light it goes down, and so on. So it is repeating, and it could be explained by the band diagram and all those things, but the important thing is, the message is, this gold zinc oxide is something like a Schottky barrier. Okay, the metal sitting on semiconductor, and in presence of light the electrons are actually increased in circuit. So this could be utilized in solar cells, in back electrode or front electrode, because in solar cell a lot of light goes unutilized, and this light can be absorbed at that cathode level, in electrode level itself. And this concept we have tried to use in hydrogen generation also, and this I will explain. You are familiar with this photosynthesis, that in the presence of light, in natural photosynthesis, the CO2 and H2O, actually in the presence of light you get the energy and oxygen, and the same thing is done in the process of photoelectrochemical splitting water. You have some semiconducting material, say iron oxide, and then when the light is shining, this electron from valence band goes to a conduction band, and it is in touch in water. So this is available for dissociating the water to get hydrogen and oxygen. But I want to increase this by presence of plasmonics. So this is what this is well known. This was well known. Okay, this phenomena is known, and people use it. Use the semiconductor as an artificial leaf to produce hydrogen. But what we tried was something different. What we said, this in the zirconium doped iron oxide is a known thing for using PEC, let us call in short PEC, photoelectrochemical splitting for water to get hydrogen. We use plasmonic layers. That means we either put at the top or at the bottom, or we sandwiched it. In either the cases we saw that there is an increase in hydrogen production. So that was a very interesting result. And then we see that a lot of groups in other countries are also trying this to increase the hydrogen production. And hydrogen is a good form of energy which you can store. Okay, so same thing we tried with other material. Instead of putting layers, we embedded actually gold nanoparticle inside bismuth bendate and iron oxide. And this material we utilized for, again, is photo spreading of water. Then again we got increase in the hydrogen production. So these were very interesting, that by introducing just gold nanoparticle, we are improving the efficiency, existing efficiency in semiconductors. So these are the possible reasons for that. One reason could be that this is plasmon resonance energy transfer. That means there is an overlap between the SPR absorption and the absorption of the semiconductor material. And the second could be related with the Schottky barriers, and these Schottky barriers are producing energy, producing electrons, hot electrons, they are going in the circuit. And the optical enhancement is also there, and this is due to scattering of photons by these large particles here. So these are the different reasons could be given for that. Now once the hydrogen is produced, then you need to store it to utilize it, or you either utilize immediately, or you use it for, you store it somewhere and then do it. So this is, we have tried graphene oxide for actually absorbing hydrogen, and then we try to determine how much hydrogen is absorbed. So this is some experiment is done. So what we did, investigation of graphene oxide and hydrogen interaction using in situ X-ray diffraction. So you have, let us come to that we introduced, there are three curves here, and you can see that this is X-ray diffraction for graphene oxide, and then when you put hydrogen 1%, 10% and 100%, then this peak is shifting. This shifting actually at the lower angle, that means the spacing between the graphene layers, graphene oxide layers is actually increasing, which is the indication that actually hydrogen is going inside, okay, in the interplanar distances. That is why they are changing. So this is, so we thought, well, it's good, it's absorbing. So we did the measurement actually. There is a technique for quantitative analysis of hydrogen in graphene oxide. This technique is called elastic required detection analysis, and this could be utilized in Delhi. There is a lab, Inter-University Accelerator Center. Anybody can utilize this facility. So here you can see in the beginning you have hydrogen which is something like this, here red, and after exposure to this, because graphene oxide also has some HOH bonds, because of that you have this red color, okay, and this is the calibration sample, this black curve. So now when you introduce hydrogen, you see depending on how much you are loading, it is going up, and then we calculated that it is going to about 6 atomic weight percent. So this is something very interesting, and we are doing more work in this direction. So one of the PhD students working in this area. Okay. Now I come to role of nanostructure and materials for nuclear reactor. In nuclear reactor, basically there are two kind of materials. One is the fissile material which gives the energy, but then there is a lot of structure material like the rods. They have to be held. There should be a lot of material inside which should be stable. It should not actually degrade. There is a vessel in which it is, everything is there. So there is a lot of controversies, a lot of discussion going on that what is the role of nanostructure in that. And there are different school of thoughts, and that requires a lot of experiments for future next generation nuclear reactors, not now. So next generation nuclear reactor, there are a lot of questions related with that. And so what we do is actually we had a project from Department of Atomic Energy. So you know, in the nuclear reactor you have fission fragments, alpha particles, neutrons. So they also affect the whatever material inside, structure material inside, they try to damage that material. So this is simulated, out of this fission fragments is having maximum energy. So this is simulated by ion beam accelerator. You shoot the ions with the energy of 100 MeV, 100 mass. This is the fission fragment mass and energy, which is available at IUC Delhi. And then in nuclear reactor, the temperature is 1000 K. So this project actually was to provide 1000 K at that. So we created this facility to do the irradiation at 1000 K. and this is what you can see from a glass window, that when it is 1000 K it is glowing, and then at the same time irradiations are done. So we created the facility for that, and now this is being used to test the hypothesis whether in the nano form it is better or micro form it is better. So those experiments are going on. It is yet to be concluded, but I don't go into details of that. I just wanted to impress upon you that it has a implication in different fields. Nanostructure and thermal storage. This is also a very interesting thing, that you can actually store the heat. Suppose you keep something in your roof, then it becomes hot. So if you put a wax can melt. There are different kind of waxes. It can melt at 45 degrees. So actually it can melt. When it is melt, then there is a lot of heat storage, because mass into the latent heat that is stored. Now it is in molten state, and when the sun is not there, you can use this latent heat, molten liquid, to supply the heat wherever you want by passing the water through a tube, which takes away the heat and brings wherever you want. So this is already being used by army in barracks, in hills, where you have all the snow all the time, the daytime lot of sun, and their temperature is -30, -40 degrees centigrade, and these are the slabs in which the wax is filled on, okay, and then that melts in the daytime, and in the night time you get heat from there. So we were doing one experiment. This is an experiment done with the mechanical engineering group. So this simple experiment is very simple. We take a very small pot in which we do melting of wax, okay, and here you see this is the time in minutes, 10 minutes, 20 minutes, 30 minutes, and this is the temperature. So you see this curve, this is for wax. It melts here, so then it is constant temperature. After melting the temperature remains constant, so it is melting here. This person, he said, I want that the energy should be stored faster. Means it should melt earlier, then it will be faster, okay. So we said, okay, let us mix the nanostructure material. So we added CNT in this, and then it is going like that. Very simple experiment, very simple experiment. And then you see it is melting earlier. It was melting at 12 minutes, now it is melting at 8 minutes. So by introducing the nano materials, we improved the power in the sense that it is actually melting earlier. That means it is storing heat earlier, faster. So such things we tried with other material. Also this is with the carbon nanosheets and zinc oxide. This is the normal wax, and then we improve in melting like this, Okay, so with this I come to this nanobiosensors for healthcare, okay. I just want to give some glimpse of different things, and this is one, you must be aware that this Sunanda, she died of, she committed suicide using some drug Alprax, so antidepressive, anti-anxiety drug, and this drug has a particular molecule which is called alprazolam, and the forensic team takes one day to tell that what is there in the blood. So what is done is that our faculty and student, they make one device which is this big, it's just a finger kind of thing, and you have 2 electrodes here, and this red color is something, a boundary for hydrophobic surface, so that blood remains here only, and then it gives signal that whether this molecule is there or not there. It's a patented, and it can be detected then and there within few minutes. So this actually, so you see that it is helping a nanobiosensor, it is helping forensic science as well, okay. So apart from this, actually we have lot of activity, and we have actually nanobiosensor for dengue, chikungunya, and malaria also, and we are trying to develop that in a single platform. We can detect dengue, chikungunya or malaria, because sometimes it is a problem which test you want to do. So in single platform is not being done so far, so we want to develop that kind of thing. We have some project for that. Cholesterol, triglyceride, and neurotransmitters, the old person disease related with this, Parkinson, Alzheimer, they are related with the certain enzymes which are called neurotransmitter, which is released from brain, and they can be detected earlier, so that cure is better for Parkinson or Alzheimer. So it could be predicted beforehand. So this kind of platform we are trying to use. That these are the electrodes for that. Okay, and this will be interfaced with the mobile and all. There is one Dr. Ashish Mathur who is doing this kind of things under some project. Okay, I'll take one result in the, I said in the beginning water and this, so I'll take one result from the water, contaminated water, let's say water from the oil industry which is contaminated with oil. So you see in this material which we used is zinc oxide tetrapod and a composite material of zinc oxide tetrapod and iron oxide. So they are combined together as a nanocomposite. When you combine, you call it nanocomposite. And this is detail how it is made, so let us not bother about this. You assume that it is available. So here in the petri dish you see this is oil which is yellow in color because of the oil. It is contaminated water. Now in this we put this nanocomposite, the black color thing you see is a nanocomposite. After 50 minutes you see the color is gone because all the oil is absorbed in these black things. The special thing about this black thing is hydrophobic. Anything which is hydrophobic is oilophilic. Oilophilic means it loves water, it loves oil. So all the oil is